All right, now we are going to discuss the correct answers to the homework from topic 1.06, number 2, which are questions 5, 6, and 7 on page 258 and 259 in our textbook. So question 5, state the non-permissible values of the variable and then solve each rational equation. Verify your solution. So our first one, A, is x plus 3 over x minus 1 equals 0. So we have x plus 3 over x minus 1 equals 0. Now in this case, our non-permissible value comes from taking our denominator and saying it is forbidden to be 0. And then we treat the not equal to like an equal to and solve for x. So x cannot be 1. Now to solve for the x value that does make this true, we can multiply both sides by that denominator, and as long as x does not equal 1, that will be perfectly valid. Leaves us with x plus 3 equals 0, or x equals negative 3. We must also verify. We verify by substituting that back into our original expression. Sorry, that's a minus 1, which gives us 0 over negative 4, which is 0, and it checks out. So 5b, remembering this time that this textbook arranges things below, not beside, we have x plus 3 over x minus 1 equals 2. So we have the same rational expression, but a different value. So again, x cannot be 1. If we multiply both sides by x minus 1, we have x plus 3 is 2x minus 2. We can bring that across. The minus 2 comes over here to become a plus 2, combined with the 3 to make a 5. Our x comes to the right, cancels one of these x's, so we have x equals 5. To verify, 5 plus 3, getting ahead of myself, for 5 minus 1 is 8 over 4, which is indeed 2. So 5b checks out. X is 5, and it's not allowed to be 1. For 5c, we have x plus 3 over x minus 1 is 2x plus 1. Still only one denominator, so x is still not permitted to be 1. When we multiply this out, multiplying both sides by x minus 1, our left reduces again to x plus 3. Our right-hand side becomes 2x squared minus 2x plus x minus 1. We'll move everything to the right-hand side and apply what we know about quadratic equations. We have a 2x squared. We had a negative x. We subtract another x, or if we want, we could think about canceling this x with this one. Either way, we have a minus 2x. And with this 3 coming over and becoming negative, that's a negative 4. So this is the same as 2 times x squared minus x minus 2, which factors as 2 times x minus 2, x plus 1. So here we'll actually have 2 solutions that make it work. Because we're getting a little cramped, I'm going to change colors for our verification steps. So we're going to check x equals 2 in blue. That's a 2 plus 3 over a 2 minus 1 is 5 on our left-hand side. And a 2 times 2 plus 1 is 5 on the right-hand side. So that checks out. And our x equals -1. I'm going to check in purple. -1 plus 3 over -1 minus 1 is a 2 over -2 is a -1 on the left-hand side. And 2 times -1 plus 1 is a -2 plus 1 is a -1 on the right-hand side. Both sides are -1, so that checks out. So both of our solutions here are valid. And in the final part of part 5, 5D, we have 3 over 3x plus 2 equals 6 over 5x. In this case, we're going to have two non-permissible values. 3x plus 2 cannot be 0, leads us to x cannot be -2/3. And 5x cannot be 0 leads us to x cannot be 0. Now we have our two non-permissible values established. We cross multiply. End up with 15x is 18x plus 12. I like to have the coefficients of my variables positive, so we'll move the 15 this way and the 12 that way. This leads us to -12 equals 3x, or x equals -4. To verify, 3 over 3 times -4 plus 2 is 3 over -12 plus 2 is 3 over -10, or a -3 over 10 on the left-hand side. And 6 over 5 times -4 is a -6 over 20, or a -3 over 10 for our right-hand side, which checks out. So x is -4. Works out well because that's not one of our restricted values. Okay, that solves question 5. Now, question 6. State the non-permissible values of the variable, and then solve each rational equation, verify your solution. So we have identical instructions, but more complicated expressions. So we will start with 6a. That is a 1 over x minus 3 minus 6 over x squared minus 9 equals 1 over 5. For our non-permissible values, x minus 3 cannot be 0, which means x cannot be 3. And our other denominator, x squared minus 9, cannot be 0. Leads to x squared cannot be 9. X cannot be positive or -3. So now we simply need to solve for our values of x. We can start by writing everything in its factored form. So x squared minus 9 is that difference of perfect squares, which works better if I copy it down correctly. Now if we multiply everything by x minus 3 and x plus 3, then we will have x minus 3, x plus 3 as denominators on both sides of our equation. So we're going to have 5 times x minus 3, x plus 3, and that is going to have an x minus 3, x plus 3. We are also going to end up eventually multiplying everything here by the 5 to put them over a proper common denominator. We'll get to that in a minute. For now, I want to focus on the algebraic variables. So this we just multiply by the x plus 3, and then we subtract the 6. Now that we see how relatively simple that is, we can multiply both sides by 5. And then when we cross multiply by our denominators, they cancel completely. So our left-hand side becomes 5x, and the 3 plus a negative 6 is a negative 3, which when multiplied by 5 is a negative 15. And our right-hand side is x squared minus 9. So this becomes x squared minus 5x plus 6 equals 0. So we need two factors which multiply out to 6 but add up to negative 5. We have x minus 2, x minus 3 equals 0. Now they laid a trap for us. The instinct here is to say, okay, x is 2 or 3, but x is not allowed to be 3. That is why one of the reasons we verify afterwards. If you divide by 3 or let x equal 3, you're dividing by 0, and that is forbidden. So x equals 2 is the only one to check. So our left-hand side is 1 over 2 minus 3 minus 6 over 2 squared minus 9. And now I'm paranoid about whether I got the minus sign. I did. We're all good. So then this becomes a negative 1 minus a 6 over a negative 5. So that is 6 over 5 minus 1, which is minus 5 over 5, or 1 over 5, which is our right-hand side. 6a checks out. (6b) z over z minus 1 minus 1 over z minus 1 is negative 4. So in this case, z cannot be 1. This left-hand side simplifies to z minus 1 over z minus 1 when we put it over a common factor. So our solutions are where 1 equals 4, which is never. So we have a restriction. We have no solutions for 6b. 6c. 5 over x plus 3 equals 2 minus 4x over 4x plus 2. So, restrictions, x cannot be negative 3 or 0. And again, we can cross multiply or just multiply everything through by both denominators. I actually prefer to think of it as multiplying everything through rather than cross multiplication because of cases like this where we have two terms being added together. With cross multiplication, it's really tempting to just bring the 4x up here and the x plus 3 up to the 2 minus 4x, completely ignoring the 2. That's not okay. We need to put everything over common denominators. So our left-hand side will become 5 times 4x, or 20x, over 4x times x plus 3. This term, with the 2 minus 4x, we're going to multiply by x plus 3. Now, with a little more forethought, we could have simplified this by saying that this has a common factor of 2. The denominator is even. We could cancel those 2's before we even began. We didn't. We will continue, because this is what a lot more students will do. Not many students will spot that simplification. And then our last one over our common denominator. So now, when we multiply everything by our denominators, all the denominators cancel. and we are left exclusively with our numerators. We have 20x. Our first numerator here multiplies out to 2x plus 6 minus 4x squared minus 12x. And our second is an 8x times x plus 3, which makes 8x squared, and then 8x plus 3 is 24x. So now we will collect our x squared terms into 4x squared. We'll move our linear x term across the equal sign to combine with our others, and we do have quite a few of those. So the negative 12 and 24 becomes a positive 12x. We add the 2, that's a positive 14x. Subtract the 20, we now have a negative 6x. And our sole constant term is this lonely little 6 here. Now we see that common factor of 2 that we could have pulled out from everything right from the start. X squared minus 3x plus 3. Because it's equal to 0, we can divide by that 2. We have x squared minus 3x plus 3 equals 0. So now, this doesn't look like it's going to easily factor with rational roots. We could apply our quadratic equation if we like. A negative b plus or minus the square root of b squared minus 4ac all over 2a gives us 3 plus or minus the square root of 9 minus 12, or negative 3 over 2. The square root of negative 3 is not a number we are equipped to deal with at this level. It is a valid number if you go to your calculator and switch either from real mode to either a plus, I think they call it bi, or to the re to the I theta modes, and calculate the square root of negative 3, it will give you an answer instead of an error. But you'll want to leave it in the real mode. That's the one that our tests are built around. So this has no solution, but it does have restrictions. So 6 part D, 2 over m minus 3 plus 1 over m is 6 over m squared minus 3m. Our restrictions are m cannot be 0 and m cannot be 3. M squared minus 3m factors to m times m minus 3. So we have 2m plus m minus 3 all over m squared minus 3m equals 6 over m squared minus 3m. Cancel our like denominators and move the 6 to the other side. And we are left with 2m plus m minus 9 equals 0. So are there numbers that we can multiply up to get 9 in some combination with a 2 that have a difference of 1 when we add or subtract? Well, if that's the case, again, our quadratic equation will serve us well. Squared minus 4 times a times c. Anytime a and c have different signs, you are guaranteed to have real roots to your quadratic equation. Doesn't mean they're going to be rational roots, but they're going to be real roots. We can stick them on the number line. So here, 6 times 9 is 54 plus 1. That is 55 over 4. So there we go. Negative 1 plus or minus the square root of 55 all over 4. These are the roots of m. So that gets a little tougher to verify. We could do numeric approximations. For example, if we said our left-hand side is 2 over m minus 3, and this gets a little confused if your variable is not x. So I will just graph it as x. There's our left-hand side. Our right-hand side is 6 over m squared. Again, I have to remember to change that to x's. Minus 3x. Here we go. And now our roots. So what values do we have here? 4, -1 plus or minus root 55 over 4. So we can have y equals -1 plus the square root of 55 over 4. Oh, right, we don't want y equals, we want x equals. So it appears we made a mistake in our algebra somewhere, as these do not actually intersect at this point. So where did we make that error in 6D? So we have the m minus 3 here, we have the m there. It's in this step down here. I treated this m as an m squared. That was the issue. This is not m squared. So the whole thing worked out to 3m minus 9 equals 0, which is only true when m equals 3, but m is not allowed to be 3, which is why when we graph it, we don't actually have any intersections whatsoever. My apologies for that mistake if that confused anyone. But that was the issue. I had messed up that one here by assuming it was going to be a quadratic out of force of habit. Anyway, for our last problem, that is number 7. So after moving the book with the video recording paused so as to not give everyone motion sickness, the Greek mathematician Pythagoras is credited with discovering the golden rectangle. This is considered to be the rectangle with the most visually appealing dimensions. This is also a carefully worded question. He's credited with discovering, they didn't say he did discover it. Turns out Pythagoras created a math-based cult and required all of his followers to attribute their own work to himself. So it's not clear to this day how much stuff that is credited to Pythagoras was actually done by Pythagoras and how much was done by his followers. Moving on, in a golden rectangle, the length L and the width W are related by the following equation. A billboard of the length of 15 meters is to be designed. If the designers want the billboard to be a golden rectangle, what must its width be? So, we have L over W equals W over L minus W, and we have L equals 15. So what would the width be? We know the width cannot be 15, because otherwise we're dividing by 0 here. That leaves us with 15 over W equals W over 15 minus W. Now we can multiply through by both denominators. Leaves us with 225 minus 15W on the left is W squared on the right. Or W squared plus 15W minus 225 equals 0. Now here we do not expect a rational answer, partly because the golden ratio, which is usually the Greek letter phi, is 1 plus root 5 over 2, and the complementary golden ratio is the 1 minus root 5 over 2. These are, so the length and width have to be in these proportions. So when we solve it, we are actually going to get probably two solutions. One width which is less than W, and corresponds to a golden rectangle with these proportions and one with these proportions. That's not the golden rectangle. It looks a little too rectangular. But those are going to be our two solutions. One for when the length is the smaller one, and one for when the width is the smaller dimension. In any event, because I know the golden ratio is irrational, I am going to go straight to our quadratic equation. So that's 15 squared minus 4 times a times c, where c is a negative 255 or 225, all over 2a. So that is a negative 15 plus or minus, and this whole thing is 225 plus 4 times 225, all over 2. We could factor out that 225 and bring it outside as 15, and there's a root 5 over 2. And these are the two possible solutions here. Okay. Now, one of them is entirely negative. So the way they had this set up already prefers which it is. And I see that now. This L minus W in the equation dictates that L is the larger dimension, because otherwise we'll have a positive number on the left and a negative number on the right. So we have a root that's exclusively negative, which makes no physical sense as the width, which means our width is going to be the length of 15 times root 5 minus 1 all over 2. So that is the dimension it is required to have. And this finally wraps up the solutions to 1.05 or 1.06, number 2.